Okay, this is the sixth video in the integration section. This is on further differential equations. So there's basically taking the differential equations that we've done previously and just looking at some sort of things a bit more complicated regarding differential equations, one or two more interesting things. And one of the main things that we're looking at here is the concept of net rate of change. So let me just illustrate this by this example. Imagine a water tank into which water is flowing and out of which it is leaking. If it flows in at a rate that is half the volume of the water in the tank, which is V, and flows out at a rate that is the square root of the volume, then we can say, we can define this differential equation, dv dt, the rate of change of the volume with respect to time, is equal to a half V. That's the rate at which it's coming in, minus the square root of V, which is the rate at which it is leaking out. So here we go. There's your water tank. There's the height of the water, the radius of the tank, stuff's coming in, going out. And in this situation, we know what the rates going in and out are in relation in terms of V. So we can define that. Now, if we look at a slight variation to that, let's say it flows in at a rate that is proportional to half the volume of water in the tank and flows out at a rate that is the square root of the height of the water in the tank. The volume, not the volume, but the height. So now here we're looking at a differential equation that looks a bit like this. dv dt equals, this is what's coming in, half V times K. This is your constant of proportionality, minus the square root of H. Now that's all well and good, but here we've got three variables in this, so this is going to be difficult to work with. But we have got a conversion between V and H. We know that the volume of a cylinder is equal to pi r squared H. So R is some constant representing the radius of the tank. H is the height, so it's effectively the volume of the cylinder of water, if you like, within the tank. So if we do this substitution for H here, just rearranging, then we're going to get dv dt equals a half kV, what's going in, minus 1 over R times the square root of V over pi. So that's now in relation to two variables, V and T. So we can process this in our usual way. Now we might also be interested in the rates of change. Here we've just applied a straight substitution. But if, for instance, we were interested in finding the rate of change of height with respect to time, or maybe maybe we want this, but we know these two. So in other words, if we know two of these three things, then we can find the other one. Now this basically is the chain rule. So I've described before the chain rule as being sort of cancellation for calculus, and that's what we've got here. So the rate of change of volume with time is equal to the rate of change of volume with height. Pretty straightforward here because it's just a linear relationship. In other models, we might have sort of maybe a sort of a curved, sort of conical kind of shape. So that might be a non-linear function. Times the rate of change of height with respect to time. So, and we'll see in the example in a moment the implementation of this sort of thing. So this is where the chain rules comes in, and so yeah, what we're really doing is expanding our dv dt into two derivatives, dv dh and dh dt, and if we wanted to collapse these back down, you can see that we've got this cancellation going on with our dh's. Okay, so let us have a look at an example, and it is in fact a water tank. Just get that nicely in the right place. Okay, so what have we got? Figure 2 shows a cylindrical water tank. The diameter of a circular cross-section of the tank is 6 meters. So therefore the radius is 3 meters. Water is flowing into the tank at a constant rate of 0.48 pi cubic meters per minute. And at time t, the depth of the water in the tank is h meters. There's a tap at t here. When it's open, water leaves the tank at a rate of 0.6 pi h, 0.6 times pi times h cubic meters per minute. Show that t minutes after the tap has been opened, 75 times dht equals 4 minus 5h. Okay. So how do we start? Well, we start by drawing a diagram. I mean, I've just cheated by copying the one across from the question, but what I've done is I've added these flow rates in, which actually are is helpful, because when we come to form our differential equation, then it's kind of easy to see what we're doing. We'll also put this relationship up here between volume and height. So this is v equals pi r squared, but the radius is 3, so r squared is 9. And I've also done that derivative, which we will need in a moment. So when we look at the differential equation that describes this, we've got dv dt equals, this is what's going in, the rate that's going in from the question, and what's going out is 0.6 pi h, also from the problem statement there. Okay, so we have got that, but again, we've got v, t, and h in there, so we need to do a little bit of conversion. Now, what do we do? Well, we're actually looking for dh dt, aren't we? So, so what would that be if we expand that out into two derivatives? Yeah, dh dv times dv dt. Yeah, so that's kind of working the chain rule backwards, I suppose. Right, because we know this, dh dv. We know dh is 9 pi, so we know that dh dv is 1 over 9 pi. dv dt is this expression here, factorized out pi here. And that's what we've got. dh dt equals this lot here. Pi's cancel, obviously. And if I multiply each side by 75, then it actually works out to what we want to show. 75 dh dt equals 4 minus 5h. Right, that's part A done. Let's have a look. When t equals 0, h equals 0.2 looks like a boundary condition, and so I'm suspecting we're going to get some integration to do here. Find the value of t when h equals 0. So indeed, we do want a relationship between h and t, which this doesn't actually give us. This just gives us dh dt with respect to h. So, so what do we do? Well, we're basically going through our process here. We're going to separate the h's onto the left-hand side and the t's onto the right side. I've also put the 1 over 75 on the right-hand side, which seemed a bit easier to me, although it doesn't actually make any difference to the end result. Okay, so then we're just going to integrate, and they should recall that 1 over a linear function of x, or h in this case, is going to be a natural log. And then this one minus 1/5 comes from this minus 5 here. So we've got that on the left-hand side, and t over 75 plus constant of integration on the right. So we can just kind of process this now, multiply both sides by minus 5. That's going to give us this on the right. This c is actually a different c to that, because it's the first c times minus 5, but it's still a constant, so I'm still going to call it c. And then finally, if we exponentiate both sides, we get this on the left-hand side. The right-hand side is e to the power of minus 2 over 15 times e to the power of c. E to the power of c is just a constant, so which multiplies this term here. So we're going to bring that out the front as a single c, although in this case we tend to use because we tend to use capital letters. In this case, then I've written a large C. So we've kind of appropriated, if that's the right word, the constant at these stages here. So this is the general solution of our equation here. It's general solution because we don't know this value of C at this point. Therefore, there are sort of an infinite number of solutions to this. But we've sort of solved the differential equation. But we now need to actually find the particular solution by applying our boundary conditions. So if we can just scroll that down there, let's have a look at this. Okay, so right. So what we're going to do is take our general solution and apply our boundary conditions by plugging in t equals 0 and h equals 0.2. Okay, so that's just going to give us all this. Obviously, e to the power of 0 divided by 15 is going to be 0, which is 1. And that's going to give us c equals 3. So therefore, our particular solution for this differential equation, given that this boundary condition, is going to be this 4 minus 5h equals 3 times e to the power of minus t over 15. And then part B, the question is find the value of t when h equals 0.5. Well, we're simply going to substitute h equals 0.5 into that equation, into that particular equation. And with a bit of subtraction and division, and I'm going to reciprocate both sides of the equation. Takes away the minus sign from there. Then we're going to exponentiate. So we're just going through our our process for solving log equations at this point. So we've got t equals 15 natural log of 2, which we can find out from our calculator is 10.40, and that's in minutes, and that's to 2 decimal places. So so that basically is our solution. So that's how that works. So I think that hopefully that is going to be it's quite useful in illustrating this idea of the net flow. This second part of the equation, really, this is just a kind of standard differential equation solving, but it's the first part of the question which really illustrates this idea of net change. Right. Okay. Let's look at another one. This is similar sort of thing. Right. At a given instant in a lake thought to contain 20,000 fish, the number of fish, n in tens of thousands, is increasing at a rate of 0.2 n. Okay, so that's 2,000 fish. So that's through breeding, through birth. Fish are dying at the rate of 0.1 n squared, and fish are harvested at the rate of 1,000 a week. Basically means that the fishing boat pulls them out at 1,000 a week. Show that the ndt is equal to minus 1/10 into n minus 1 squared. Okay. Right. Well, let's have a look at the differential equation that's defining these. So we've got net rate of change here. So the rate of change of the number of fish, all in tens of thousands, of course, is equal to 0.2 n, that's from the question, minus 0.1 n squared, again, minus 0.01, that is the 1,000 a week that's being fished. Right, okay, so now it's just really a simplification process, and we just factor out minus 0.1, which is minus 1/10, isn't it? We're going to get this minus 1/10 into n minus 1 squared. So so that's what we've got there. So that's part A done. Part B, solve this differential equation giving the answer as n is some function of t. Again, we've done our process of separation. We've got the n's on the left, the t's on the right. And yeah, if we just integrate this, we're just going down this process. This is just the power rule going down here. We get to this point, then if we reciprocate both sides, we get n-1 equals 10 over t plus c, and therefore n equals 10 over t plus c plus 1. Now, if we now apply our boundary condition, this is not untypical. The boundary condition in this question is not that obvious. You have to kind of glean it from the text, but it does say at a given instant, and this is our starting instant. So we're looking at time going forward from this. The lake's thought to contain 20,000 fish. So basically, our boundary condition is this: when t equals 0, n equals 2, 2 being 2 in tens of thousands of fish. So we can just pop those into that equation, and we work that through with a bit of algebra, and it gives us c equals 10. So n is going to be equal to 10 over t plus 10 plus 1. And if we rearrange that, we're going to get n equals t plus 20 divided by t plus 10. So that is part 2. That is our differential equation with n explicit expressed as a function of t. There we go. I've rewritten it here. So for part C, we're going to find out after how many weeks the number of fish will drop to 16,000, beg your pardon, 250. So yeah, so we're just solving this equation, aren't we? 16,250, that's our n, is equal to this. And yeah, so we're just going through, cross multiply this denominator up to the left, and then solve for t, and that's going to give us t equals 6 weeks. Okay, so that's okay. And then the last part says, state the long-term prospects for the fish population. So, yeah, now if we go back to our original equation, I think the thing with the differential this differential equation is it's in this case it will give us an indication of when the population is unchanging. And if we look at when dn dt equals 0, that's going to imply that n equals 1. Okay, so 1 being 10,000 in terms of fish. So essentially, this is what's going to happen. So once we've got to that point, we're really adding and taking away from fish at the same rate or the same amount every week. So it's therefore it's going to stabilize at 10,000 fish. So that's that is that. So yeah, so it's quite instructive, I think, to look at this. Depends on the differential equation, but usually for the first order linear differential equations that we're interested in, then we should be able to draw that conclusion. Other differential equations, as we'll come to shortly, are rather more complicated, and it might not be possible to easily see that. Okay, so a couple of examples there that I think should be pretty helpful. Let's just have a look at one or two other things in relation to differential equations that we might come across. I mean, epidemiological models. I mean, there was a lot of kind of use of this and thinking around this sort of thing, obviously, during the sort of the height of the COVID pandemic. So if we can imagine this sort of model where we've got a fixed population of people, of whom people are either susceptible or they're infected. I mean, this is a simple model here. We're assuming that simple people, in the simple model, that susceptible people get infected as a result of some contact with infected people, and then after a while they're not infected and they go back into this pool of susceptible people. So here we go. So if I is the number of people infected in the fixed population, P, S is the number of susceptible people, then yeah, so the number of people infected is going to be, well, this is what it's increasing by. So that's what's going into this box, if you like, here. And then this is what's coming out due to recovery. Now, how do we calculate the rates, the rate of infection? Answers on a postcard, basically. But how this is kind of viewed as a sort of a bit of a simplification is that it's actually proportional to the products of the number of people infected and the number of susceptible people. So that sort of makes sense, doesn't it? Because it's if we've got a lot of infected people but not many susceptible, then we would expect the rate to slow down. So, and the other way around, there's not many susceptible. There's lots susceptible, but not many infected. Then it's going to start to increase slowly. So it's a kind of fair assumption that it's going to be like this. It's going to be a function of the two numbers, but whether or not it's the product, I think you need further study on this. But if it's proportional, then we've got our constant of proportionality. So we've got this K times the number of infected times the number of susceptible. Okay, and then what about the rate coming out of the infected pool, if we can call it that? It's going to be proportional to the number of people in here. If we assume that it's like a fixed number of fixed number of days that people are infected for, perhaps assume whatever the average is, and that's going to it's going to give us this. So this is some constant, the recovery rate constant times the number of infected people. So so we've got this differential equation describing this model, and of course this number of susceptible people is this constant population minus the infected number of people. So we do have a relationship between di dt in terms of I. So this is the sort of thing that we might be expecting to solve. Now, in actual fact, this the solution this is not quite straightforward. I'm not going to cover it here. I'd have to. That's in a separate video. Because it does involve this partial fractions process and kind of solve it through that process. So it's a little bit kind of messy, but yeah, we can solve that and derive a differential equation and solve the differential equation so that we've got I in terms of t. Okay, and you would get a general solution, and then if we've got a boundary condition like at time t equals 0, we've got 10 infected people, then we could actually look at the number of infections after so long after t equals 0. Now that's a pretty simple model. It's perhaps a bit unrealistic, really. Why? Well, first of all, P isn't constant, is it? I mean, the population is changing all the time with births and deaths. Recovered people, they have some immunity for a period of time, don't they? So if we want to make that a bit more realistic, perhaps we have to make some assumptions about that. Not everybody recovers, of course. Some people actually die as a result of the infection, and then once people are in some kind of recovery immune period, then they may die during that period as well. We've not taken into account immunization either in here, so that, you know, there's a few things we can do to make it more accurate, but obviously in the process of doing, we're making it more complicated. We also, you know, with a more complicated model like this, we might end up with not just one differential equation that we model out of this, but a system of differential equations, and then the solution to that is more complicated and beyond what we're doing in A level. Now, this particular thing, we've got the S, we've got the I, we've got the R. That is described as the SIR model for infectious diseases, or the epidemiological model, the SIR model. So you might be interested actually to go and root this out, because there's quite a lot of resource on the internet that will tell you about this. And if you're interested, then, you know, go away and study that. You might find as well, if you're actually thinking of going into a career in medical research, and anything to do with medicine, that knowledge of this is actually going to be quite useful. And perhaps more to the point is if you can demonstrate knowledge of this in an interview, then that can only be good. Right, so that's something. So no examples there, because they're a little bit more complicated to work through and a bit messy. Let's just have a look at one or two other things before we finish this video. Now here's a solution. There's sort of an exponential kind of model, that comes from dy dt is proportional to y. Okay, so if we got that, and then we put our constant proportionality in, and we went through our process, we'd actually find that this is the resulting general solution. Now, we should note that this actually, if you can recall transformation of graphs, that this graph is actually a transformation of this y equals e to the power of t. We've got an upward stretch by y0, and we've got a horizontal stretch by or squash by k. So that is something that you might need to be aware of in some forms of problem. Similarly, if we've got this y equals sine t plus cos t, this can be restated as that. Okay, this is the R formula, or the so-called R formula, but basically what it is just the fact that linear sum of sines and cosines can be defined as a stretched, shifted sine or cosine curve. And that itself, of course, is a transformation of that, stretched up by vertically by √2 and shifted horizontally by pi over 4. So again, that might come into some of these questions. So there'll be other example worked example videos that you can refer to on these. Another point on boundary conditions. Now, all the cases that we've tended to look at have been ones where we have an initial condition. So some value when t equals 0. Now, if we're looking at this sort of model here, this sort of exponential model, what that means is we can actually solve for y0 first, and then we'll have another boundary condition, which then we can use in this modified differential equation, because we've already got one of our constants, but then we can resolve for the other one at k. That's kind of pretty typical situation. However, it's not necessarily going to be the case, because you might well find that, yeah, you've got two boundary conditions, but neither of them is an initial condition. And if that is the case, what you're going to do is end up with two equations in y and t, where you've substituted in the relevant values of y0 and k. So you've got two equations in two unknowns. But of course, panic not, because we've essentially got simultaneous equations, and we can bash those together to resolve for both of the unknowns. So yeah, watch out for that. Just the only other thing is, this video is called Further Differential Equations, but it's only further differential equations in the context of A-level maths, and the field of differential equations is very large, and this, for instance, is a differential equation. I don't know how solvable this is. I just kind of made this up, but this could actually represent some real life situation, and there are lots more techniques for solving differential equations, and certainly more complicated differential equations. At some point, our analytical methods, apply rules of maths, cease to actually work with these things, and we may have to have recourse to numerical methods. So if you've done things like Newton-Raphson and so on, well, there are equivalent techniques for solving differential equations, and so we might need to look at those, but again, that's not at A level. But just to say, it's a very large area of study, and again, if you wanted to and you were interested to actually take it further, then there are plenty of resources available that would help you study differential equations. And this sort of thing, very important in engineering. You would, if you're going into any engineering disciplines, then you will be doing more work with differential equations. Okay, so that is further differential equations. Hopefully that's given you a bit of an insight into some of the kind of more complicated things that you might need to do with differential equations, and gives you some ideas as to how to solve these problems. So thanks for listening, and I'll see you next time.